How AI fraud detection catches synthetic identity fraud. Welcome back. Today's topic is how AI fraud detection catches synthetic identity fraud. We'll cover what you actually need to know about AI fraud detection. Next up, let's talk about why synthetic identity fraud slips past manual screening. Manual KYC reviews look for document inconsistencies and known watchlist hits. Synthetic identities present clean documents and pristine credit histories, which is exactly why they pass. The fraud pattern is deliberate. Criminals spend months credit farming a synthetic profile, making small purchases and paying them off until the account qualifies for high credit limits. Then comes the bust out, every available credit line is maxed and the fraudster vanishes. No single data point in a synthetic profile looks wrong. The social security number might belong to a minor or an elderly person who rarely uses credit. The registered address is real. The phone number is active. Manual reviewers cannot catch a profile engineered to look legitimate over an extended period, and they certainly cannot do it at scale when processing hundreds of applications per hour. U.S. lenders lose an estimated $6 billion annually to synthetic identity fraud, a figure that has grown steadily as digital account opening removed the friction that previously slowed these attacks. More troubling for compliance teams, the same profiles used for credit fraud frequently reappear in AML investigations months later, repurposed as money mule accounts once the credit damage is done. Next up, now, how AI fraud detection catches what humans. Mississippi AI fraud detection works because it evaluates data points in relationship to each other, not in isolation. Machine learning models build a probabilistic picture across hundreds of variables simultaneously, and synthetic identities have behavioral and relational signatures that deviate from real applicant patterns in ways humans cannot process at the speed required. 3 mechanisms are most effective. Graph-based network analysis. Real people have organic connections, addresses shared with family members, phone numbers associated with a household over years, email accounts linked to actual subscriptions. Synthetic identities tend to cluster around a single SSN with multiple fabricated names or share infrastructure like temporary phone numbers and prepaid cards. Graph analysis maps these relationships and flags applicants showing unusual network sparsity or suspicious co-registration patterns across institutions. Now, moving on to the explainability problem, why black box models fall short. This is where most fraud teams run into difficulty. A model that accurately detects synthetic identities but cannot explain why it flagged a specific applicant is a regulatory liability, not an asset. Explainable AI in fraud detection means models and supporting infrastructure that produce human-readable justifications for each decision. In practice, a compliance officer reviewing a flagged application should see something like, "This application was declined because the SSN had 3 prior associations with different names over the past 24 months, the registered address has no utility payment history, and the device fingerprint matched 2 prior decline applications at this institution." Without that explanation chain, institutions face 3 specific problems. First, regulators cannot assess whether the model discriminates based on protected characteristics. Second, compliance teams cannot write defensible suspicious activity reports. Third, CISOs cannot demonstrate to auditors that the model behaves as documented between validation cycles. Next up, what AI fraud detection looks like in a compliant architecture. Building a compliant AI fraud detection architecture means layering 4 components. Feature engineering pipeline. Raw data flows into a feature store where it is normalized and enriched with third-party signals, credit bureau data, device reputation scores, and network relationship data. The feature store must itself be versioned, so that the exact features used to make any historical decision can be reconstructed during an audit. Ensemble model layer. Most production fraud detection systems run multiple models in parallel, a gradient boosting model trained on historical fraud labels, a graph neural network processing relationship features, and an AI anomaly detection banking model flagging deviations from established behavioral baselines. Each contributes a weighted score to the final output. Production systems need to make these decisions in under 200 milliseconds to support real-time transaction approval flows, which places real constraints on model complexity. Let's talk about now, AML automation and AI fraud detection, where they overlap. Synthetic identity fraud and AML are not separate problems at the system level. Synthetic identities are frequently used to open accounts that later receive proceeds of organized crime, human trafficking, or structured cash deposits. A synthetic account that ran clean for a year is a ready-made money mule, and AML automation AI needs to treat it accordingly. The approach is to run transaction monitoring logic against synthetic identity flagged accounts with tighter velocity thresholds than standard accounts. When a high-risk account receives multiple small transfers from different originators within 72 hours, a behavior consistent with structuring, the system escalates immediately rather than queuing it for weekly batch review. The critical gap in many institutions is the separation between fraud detection and AML transaction monitoring. These often run on separate platforms with separate risk scores that don't communicate. A synthetic identity flagged but not rejected at onboarding may not carry that risk signal into the AML monitoring system. Institutions that have unified these signals so that fraud risk scores populate AML risk profiles report substantially fewer false negatives in SAR investigations. Now, let's talk about meeting regulatory model transparency requirements. Regulators across jurisdictions are converging on similar expectations for AI fraud detection systems, even if the specific frameworks differ. The difference between a bank that passes a model risk examination and one that fails usually comes down to documentation depth. A well-performing model with incomplete records will fail an OCC or PRA review just as surely as a poor-performing one. Practically, this means compliance teams need access to a model registry that stores model versions, validation reports, and change logs. Fraud detection machine learning systems without this infrastructure cannot meet SR 11-7 requirements in the US or equivalent EBA ICT risk guidelines in Europe. The BIS guidance on model risk management provides a useful international baseline for what sound practice means in this context. Let's talk about now, false positives, the part nobody wants to talk about. No AI fraud detection system ships at optimal performance. Models trained on historical fraud data will generate false positives until they are calibrated against the institution's specific applicant population and transaction mix. A 2% false positive rate sounds manageable until it applies to 500,000 monthly applications, that is 10,000 legitimate customers wrongly declined or delayed. That has both revenue and regulatory implications. ECOA adverse action requirements mean each wrongful decline needs documentation and, in some cases, a specific explanation that is intelligible to the applicant. The practical approach is risk-tiered decisioning. Now, moving on to conclusion. AI fraud detection has become the practical standard for catching synthetic identity fraud that manual KYC processes cannot handle at scale. The combination of graph analysis, behavioral machine learning, and real-time scoring lets financial institutions flag fabricated profiles before losses are incurred, not during collections 6 months later when the bust-out is already complete. The explainability requirement is not a regulatory box to check, it is what makes the system defensible over time. Every declined application, every SAR filing, every analyst override needs a documented evidence chain. That is what compliance officers and regulators need, and what modern fraud detection machine learning architecture should produce by default, not as an add-on. If your institution is evaluating AI fraud detection systems or working to close the gap between model performance and regulatory model transparency requirements, the 4-layer architecture described here is a practical starting point. Building explainability in from day one is considerably cheaper than retrofitting compliance documentation into a black box system under examination pressure. For risk heads looking at how AI fraud detection fits into an enterprise-wide strategy, Card Fraud Analytics and AI-powered detection strategy for risk heads covers how these detection layers connect at the portfolio level.